Hi there, I'm Watson. I'm a software engineer at Google and a maintainer of the Rust for Linux project. Today I'm going to tell you a little bit about this project, um, what we're doing, why we're doing this, how we're doing this, and along the way I'm going to show you a few examples that showcase the interfaces that we built for as part of this project. Um, and then we're going to talk a little bit about some of the challenges we faced during this project, and I'm going to finish up with our plans for the future. So let's get started. What is it that we're doing? Okay, we're making Rust a first-class language for Linux kernel development, and what I mean by that is we want Rust to be fully integrated into the build system, the testing tools, integration, and all infrastructure related to the development of Linux kernel modules. And the idea is that eventually we'll get to a state where where a developer can decide which language they want to use. They can pick C or they can pick Rust for their new projects. And then once we describe this to people, a natural question that follows is why would we want to do that, given that C has been used successfully for over 50 years to develop kernels. As some background for that, the first thing we'd like to discuss is the Linux kernel itself. It's widely used. It's used in embedded devices, in mobile devices, laptops, desktops, servers, supercomputers. It's used in billions of devices, so it's widely used. Another aspect of this is that it runs in a more privileged mode than most applications, which makes it a prime target for attackers. And vulnerabilities in the Rust kernel usually result in high severity issues. So in the slide, we actually have the number of bugs found each year over the last 10 years. And if you look at 2022, we already have 122 vulnerabilities found this year, which means that even if we stop today finding vulnerabilities, if we find no more vulnerabilities this year, we still have at least one vulnerability every 3 days found in the kernel. And this is where we think Rust can improve the situation. Estimates show that between 70 and 80% of these vulnerabilities are due to memory safety issues. And Rust eliminates these classes of vulnerabilities by construction. Okay, so if one chooses to write new code in Rust, they'll know that these vulnerabilities will not exist in their code. And they can do that without affecting performance. And since Rust has a richer type system and it's a more modern language, it allows other classes of bugs to be found at compile time too. So it improves productivity. And we'll see a few examples of that in the following slides. But before we go into that, we'd like to discuss how we're doing this. Okay, the first thing, and the strategy for doing this is this: we integrate with the build system, meaning that we allow people to write Rust source code, and that gets compiled and linked into the system. And we use BindGen to go through the C header files from the C side of the kernel and generate Rust versions of those. And lastly, since we don't want people to call those functions directly because those calls would be unsafe, we implement safe abstractions for these C functions around subsystems. And that's what we want developers to build on. And our expectation is that we'll have very little, if any, unsafe calls when developing Rust code in the kernel. So let's go into a couple of examples that will give you an idea of what these interfaces look like. The first example is interrupt handlers. In Rust, this is how one would implement a interrupt handler. The top part is the handler itself. The bottom part is how we register with the interrupt subsystem that we are interested in handling some interrupt. And as you can see highlighted there, one thing that you have to do is you have to specify the type of data that is attached to your handler, the context data that is attached to it. And in C, for example, this is not done this way. In C, you have no way to declare a type and then have functions have different arguments based on that type, you have to cast. Usually use void star arguments and you cast them. And this is of course unsafe because code can get out of sync and can result in memory issues there. In Rust, we don't have that. We declare the types, and the type declared in the handler dictates what the type is that gets called in the handler function, and what type of data you need to pass when you register. And you can see there in the bottom of the slide, highlighted data. The type of data there is ref NVMe-Q, which in this case is a ref counted data structure. Another aspect of this that we feel is an improvement over C in terms of productivity is that the registration has a destructor or a drop implementation that automatically unregisters when it goes out of scope. And related to memory safety here, data in this case here is actually becomes owned by the handler, which means that it's guaranteed to be alive while the handlers are being called. And when the registration is being destructed, we first unregister and ensure that no more handlers are running, so the data is not being used. Then we destruct the data, which in ref counted case means that we just decrement the ref count and free it if it goes to 0, and if it's just a regular pointer, it gets freed, just freed automatically. So this is the first example. The second example has to do with reference counting of C data structures. In the kernel, we have lots and lots of data structures that are ref counted, and here in this slide we have a few of them. And in the first column we have the name of the struct, and in the second column we have the function that is used to increment the ref count, and on the third column we have the function that is used to decrement the ref count. In addition to finding out what these functions are to increment and decrement, developers also have to follow a discipline. For example, when they're done using the pointer, if they own an increment in the ref count, they need to ensure that they decrement the ref count so we don't have leaks. And when they're holding on to pointers that are passed to them, they need to increment the ref count. Otherwise, they may end up with dangling pointers. And they get no help from the compiler in doing this on the C side. But as we'll see in the following slides, Rust helps us with that. So here's an example of using reference counted files in this case. We have a create function that just creates some file and returns a pointer to the file that is that owns an increment in the ref count of file. And then the takeover function actually takes one of these pointers as argument. And the idea here is that it's called takeover because it takes over that increment of the ref count, which means that it is itself responsible for decrementing the ref count. And you can see here that in Rust, in this example, it's just an empty function. However, the drop implementation of aref, which is the destructor, automatically decrements the ref count for us. So this is one source of mistakes that would lead to memory leaks that Rust helps us with. In the example 1 function, we see takeover being called, but the argument that example 1 takes, f, is just a shared reference to a file. So it doesn't own the increment of a ref count in file. So we cannot here call just takeover f, because takeover expects a owned increment of the ref count. So we call this method called into, that converts a shared reference file to an owned reference to file, and which means that takeover can then decrement the ref count when it chooses. So this is another way that Rust helps us here. If we call a function that expects to take over the reference, and we don't actually pass it an owned reference, it won't compile. And in example 2 here, we have another example of calling takeover, but here instead of calling into, we call clone. And the reason we call clone here is because we already have an owned reference. So what clone does is it increments the ref count, and then takeover gets called. So it's similar to the previous one, but we use a different method because we have a different object type to convert. Now, since f is the return value of create, it's already itself an owned reference. So we could have just called takeover with f. But if we had done that, then we wouldn't be able to use f afterwards, because we would be handing over the reference that we owned to take over. And if we were to do that, the compiler would catch it and not allow us to compile this code. It would complain that ownership of F was transferred to takeover, so we shouldn't be able to use it. So this is another way in which Rust helps us here with safety, right? If we make this mistake of transferring ownership of something to a function, then we're not allowed to use it afterwards. And if we try to do it, then compilation fails. And lastly, about these file examples, we have this ~f, which converts a owned reference into a shared reference. And this is how we call example1. If we try to call example1 by just passing f, it wouldn't compile because the types are different. Now, this is it for using files, ref-counted files in Rust. Now here we have the same code, but instead of having files, we have tasks, right? So what we want to show here is that the way we do ref counting of C data structures in Rust is consistent for all data types that are ref counted. So all the code that we had before for file is also usable here for tasks. So what does this sort of abstraction offers us, right? And this ties us back to our discussion before of why we're doing this. The first thing that gives us is safety. Right? So if we stick to the safe dialect of the language, which is what we did in the previous slides, then we're guaranteed to have no dangling pointers, no use after free issues, which amount to 70 to 80% of the vulnerabilities that we find in the kernel and other C-like projects. It also improves productivity because we have a consistent way to handle ref counting of these objects. We don't have to try to first find out whether an object is ref counted and how to increment, how to decrement the ref count. Those are all consistent across all types. And this also improves productivity because we don't have to remember that we always need to decrement the ref count. And we know that if we pass ownership from one function to another, then we know that the compiler will prevent us from using the object again. And lastly, the performance aspect of this. What is important here is that, important to realize here is that these abstractions actually zero cost. So all of this abstraction is actually compiled out of the way and turned into C calls by the compiler. And in fact, when LTO is enabled, these may even be inlined. So they're not even C function calls. They are just instructions in the instruction stream for those functions. And this is what I had to tell you in terms of examples for Rust in the kernel. Now let's talk a little bit about the challenges that we faced while working on this project. First, I'd like to tell you about some of the technical ones. And the first one is self-referential data structures. In the kernel, we have lots of them. For example, list heads. They are circular, doubly linked lists, which means that they have pointers to themselves. The entries have pointers to themselves, either directly or indirectly. But those pointers are there. And this is actually something that is very common in the kernel and used to build a lot of other primitives. Now, the difficulty for us with Rust is that Rust expects all data structures to be movable. And by movable, I mean that we can copy the contents of these data structures bit by bit from one location to another. And in most cases, this works fine. But when we have self-references, then we end up with dangling pointers pointing to data that was moved. And this is exactly the sort of thing that we want to prevent. So we can't allow this when we're dealing with C structs. And the way to avoid that on the Rust side is to use pinning. And pinning comes with lots of challenges in terms of ergonomics. So at the moment, we require additional unsafe blocks when we're initializing mutexes, for example. But the good news here is that we actually think we found a way to avoid this and not require changes to the language. So we're working in a solution for that. The next big challenge we had was that BindGen doesn't handle non-trivial macros and inline functions. And we have lots of those in the kernel, mostly for performance. Before we had LTO, lots of functions were declared in header files. as inline functions, such that they would be inlined on the C side if the compiler decided to do that. And bindgen doesn't handle those functions, which means that every time we want to use one of those, we have to write manual bindings ourselves, which gets in the way. But it's not show-stopping, but it gets in a little bit in the way. And the last thing that we'd like to point out as technical issues is unstable features. We actually use several unstable features of the compiler at the moment. For example, we have a different implementation of arc, which we call ref, because we want different behavior in ref counting. The kernel itself has an implementation, and we want to use that implementation instead of the Rust one due to different behaviors. And we have a few other places where we need these unstable features. And the problem with needing these unstable features is that we cannot just declare a minimal compiler version and allow people to just use any compiler starting from that. We actually have to mostly stay with the latest and greatest stable version of the compiler. Over time, we want to move away from these unstable features, either by stabilizing them or finding different ways of doing things. And then once we reach this state where we have no unstable features, then we can do this thing where we declare what the minimal version is and just use that. And then people will be able to use the compiler version that is shipped with their distributions, for example. In terms of not as technical challenges that we faced, the first one is that some developers are still skeptical about Rust in the kernel, right? They either don't see Rust as an improvement, or they think the risks of adding Rust outweigh the benefits. And so we're trying to have discussions with these developers, and we're trying to get to the core of the issues. But another thing that we're running into is bike shedding. While having these discussions, a lot of the discussions actually end up being discussions about the coding style. Should we mimic the Rust style, or should we use the Linux kernel C style, something similar to that? And some developers find that the syntax of the language is unreadable and things like those. So the discussions sort of like lose focus because of these issues that are not all that important and don't come to the core of the benefits that Rust brings and the risks. So we're finding some difficulties in getting through to those things, and something we need to work on. But the last aspect that I flagged as not as technical is the lack of support for all architecture. The kernel actually supports lots of architectures, but LLVM doesn't support all of them. So I claim that this is not as technical, despite having lots of technical aspects to this, because we actually have several fronts in which we are addressing this. Other people are helping us address this issue. One of them is a front end, a GCC front end for Rust. And this has actually been approved by the GCC steering committee. And what that gives us is, once it's ready, it will give us the ability to use GCC, which actually supports all the architectures that the kernel supports. So this would go away once that project is finished. We also feel that once this is upstreamed, this effort is upstreamed, then the owners of these architectures will actually be encouraged and will have an incentive to go work with the LLVM community to add support to the LLVM backends, such that the architectures will be automatically supported in kernels compiled with Rust support. So the last thing I'd like to tell you about today is what it is that we're doing next. Okay. So the first thing is upstreaming this Rust support that we've been working on. At the moment, we have a clone of mainline, and we add our patches to that clone. It's available on GitHub for anyone to clone and contribute and look at it if they so choose. And we, of course, keep this up to date with mainline. Every time there's a new release, we rebase on top of that version. And what we want eventually is for this to be upstreamed into mainline kernel, which will mean that anybody who wants to build Rust code can just get the support automatically by cloning any any version of mainline kernel and kernels that are derived from that, which is basically most kernels. So this is the primary thing that we're working on. The next thing is working with maintainers, and the idea here is that we want maintainers are obviously better positioned to write these abstractions because they've written the C version and they understand all the issues and they know the kinds of mistakes that people make while using their subsystems. So we went to work with them, and what we can bring is some of this experience that we've had in building these other abstractions. So we know the ways in which we can leverage the Rust type system to catch mistakes earlier. And so this is something that we're looking to do. And even for subsystems that already have some of these abstractions, we still want to work with maintainers to make sure that we cover all the scenarios and we get the feedback from them on what could be improved. And lastly, we also want to work with all the developers that want to use these abstractions that we are building. And the idea is that we fully expect for there to be some rough edges in these abstractions, because when we build them with a specific scenario in mind, and when people try to use this for different scenarios, they may run into issues. So we want to hear about those, and we want to help people address those issues. And of course, we want to use this feedback to then update our abstractions and improve them, such that the experience will be better for developers coming afterwards. And lastly, we also understand that despite having some samples, we don't really have a lot of resources that people can use to learn how to write this code. So our plan is also to work on producing some material for developers to be able to learn how to write this code and get up to speed quickly. That was all I had. Thank you for watching and have a great day.